Let me start with a few announcements, one of which is here. The 2021 version of the New Zealand program is having an information session this week, Thursday this week, here at noon. So if you're interested in learning more about the New Zealand program, please come to that information session. There'll be another opportunity in February. Before we get started, so I've got a few more announcements. One is that we will be having lab today, Tuesday, 1 to 3 and 4 to 6. So the later afternoon shift has been shifted to 4 to 6. Let's see. Your problem set, which you turned in over the weekend, has been graded, but I'm not going to turn it back today. But the grades are on Moodle. So if you're curious about how you did, you can look on Moodle, and the papers will be available to you tomorrow or Thursday. Quiz 1 is available now. It's due on Sunday. Same deal, you pick, well, in this case, you pick up the quiz at the desk. Don't go anywhere with it, and don't go very far with it. Sit down, take it, and turn it back in at the desk. It doesn't leave the building. You can go someplace, it doesn't have to be right out here, but, you can take it someplace conducive to doing the quiz. But remember, the quizzes are closed book, no collaboration. Trusting you to, remember academic integrity and do it that way. The material on the quiz is anatomy, cellular and body anatomy. So the sources of information to study for the quiz are the coloring book, obviously. So coloring book assignments through this week are fair game for the quiz on Sunday. I mean, you can take it any time, but it's due on Sunday. But the assignments are the ones through this week, through Thursday this week. The worksheets from the lab are your friends here in terms of remembering the names and actions of muscles. The worksheet is available. Obviously, those of you who have lab today will get the worksheet today, and will get answers today. A copy of the worksheet is copy of the blank worksheet is available on Moodle, and my answers to the worksheet will be available on Moodle tonight after lab today. If you have a question about whether something that is in the book could be on the quiz, the key concepts list is your guide. So for example, I'm just looking on page 21, which is one of the coloring assignments that it's terms of movement. So extension, you could wonder, is the word extension a word that could be on the quiz? Well, let's look it up on page 2 of page 3, the anatomical terms includes the word extension and extensors. So yes, extension could be on the quiz. But it also has the words inversion and eversion. Okay, you've heard those words before. Is it on the list? No. So you don't have to worry about inversion and eversion. Okay, so there are words in the coloring book that are not on the key concepts list, and those should not dominate your study. Okay. Questions about the quiz? Anyway. Put your electronics away. Just put it away. Even, if someone sees you doing the quiz and your phone out, even if you're just texting a friend about, going out that night, that's against the rules. That's a violation. So don't do that. I think the quiz will take you about a half an hour. Yeah.
You said the coloring it's through Thursday, that'll be?
The coloring assignments that are in this course schedule through Thursday are fair game for the quiz. Other questions? Lab, quiz, problems. Craniotomy. So we're going to be opening up the skull and taking out the brain this coming weekend, Sunday 2 to 4. This is optional, recommended, because it's an incredible thing, but it's optional. I'll make another announcement about that in lab and on Thursday. Okay, let's turn our attention to what we're doing today. We're going to build on your knowledge from cell phys and talk about synaptic potentials, excitatory and inhibitory postsynaptic potentials. So I will use this jargon, EPSP and IPSP, without translating it because it's just part of the language. EPSPs are depolarizations, excitatory postsynaptic potentials. And IPSPs are hyperpolarizations, inhibitory postsynaptic potentials. So we're going to talk about those today. You did some work on those on the problem set, so you're primed for this. Then we'll turn our attention to action potentials, and we'll talk about channels responsible for action potentials, building on what you learned in cell phys. So basically, you've been learning about membrane potentials, let's just say in the cell body. Now we're going to be talking about synaptic potentials driven by neurotransmitter release from a presynaptic terminal, but we're going to be looking at postsynaptic potentials. Then we'll be looking at action potentials propagating along an axon, and then on Thursday we'll talk about what happens at the presynaptic terminals. So, yeah, that's the way it's going to go. So I should have put this slide up. We've been talking about this, membrane potentials of this neuron. Now we're going to be talking about membrane potentials, either excitatory or inhibitory potentials, information coming into this neuron, whether it's at the dendrite or at the soma. Then we'll talk about the action potentials being generated by that neuron, and then the neurotransmitter release here, which is really the same principle as the neurotransmitter release here. So we're going to circle back to the presynaptic terminal. Here are some key things. Synaptic potentials, both EPSPs and IPSPs, are small. They're local. They add up. They summate, both in time and in space. We'll talk about temporal and spatial summation. Action potentials are large, so-called all or none changes in membrane potential, and they propagate further because of the properties of axons. So here is this is a slide from your cell phys book. Let's just get oriented. Here's the membrane, cell membrane. Let's just say we're in a soma. Well, let's just say we're in a dendrite where there are lots of receptors. The membrane potential is negative on the inside because it's at rest. And you've done problems related to the resting membrane potential, and you know that it's negative and why it's negative and why it's not all the way to EK, but why it's still negative. At an excitatory synapse, that is to say a synapse that expresses excitatory receptors that are permeable to cations, especially sodium, activation of the receptor by the neurotransmitter allows sodium to flow in, which causes less negative in, which is a depolarization. and you did this in the problem set. At an inhibitory synapse that expresses a different type of receptor. So let's just go back. This, this isn't a very good illustration of it. Let's go back to this one. Let's just say that this synapse from this cell is expressing an excitatory neurotransmitter and excitatory receptors. That coupling of excitatory neurotransmitter and excitatory receptors happened, that the expression of that happened during development. Cues were done when that pairing was made, when those nerves were connecting to each other during embryological development. That told, okay, what kind of neurotransmitter is going to be released, what kind of receptor are we going to express here? That was done during development. And let's just say that this synapse from a different cell is inhibitory. So different cues, different signals happen during development, and this part of the membrane right here expressed inhibitory receptors, and this presynaptic terminal expressed inhibitory neurotransmitters. That pairing was done during development. What we're talking about here is physiology, not development. The mechanisms of this development are very complicated. Developmental neurobiology is a whole course, which is not this course. Anyway, at an inhibitory synapse, a different neurotransmitter activates a different receptor. And in the problem set, you learned about GABA A receptors, chloride channels, chloride influx, causing more negative on the inside. Chloride being an anion, negative charge flowing in, more negative inside, more polarized or hyperpolarized membrane potential. But that's not the only way we can get hyperpolarization, which, as you learned, you can activate a potassium channel. So more potassium leaving through potassium channels would also make for a hyperpolarization. That was in the problem set. Yeah?
Could an excitatory synapse also hyperpolarize, or you don't need depolarize?
So you learned in the problem set that an inhibitory synapse can sometimes be, under certain circumstances, can sometimes not be inhibitory. I am not aware of a good example of an excitatory synapse being not excitatory. I'll bet there is one, just because there's an exception to every rule, but I can't come up with it right now. So here's a cartoon from your textbook of an excitatory postsynaptic potential, EPSP. Here's the membrane potential, here's the resting membrane potential. You know all about this, the Nernst potential, the Goldman-Hodgkin-Katz equation could be used to define the resting membrane potential. This is a cartoon, it's at -70, because that's typical, but there's resting membrane potentials of -75, -80, -65. This is just typical. At this point, neurotransmitter was released, and it activated these types of receptors, causing a small local depolarization, which has a sort of a characteristic time course, a rapid-ish depolarization, and then an exponential decay back to its baseline. We'll talk about threshold in a minute. So, EPSPs, like I said, are small and they're local. So this cartoon is illustrating the site of the membrane where, this one, I didn't give this to you because you don't, this is sort of, the detail here is not necessary to have on your hard copy. This is where the neurotransmitter activated this channel. Influx, there's a depolarization here because of the influx of cations. That is local. That is to say, it spreads, but it doesn't spread very far. So if this is the site of the synapse, and this is the small local depolarization there, and actually this scale is bad because this shouldn't be as high as this. Right? This is not 0, this is minus 50. Here's the local depolarization that spreads in space. And as you go further away from the site of the channels, the depolarization gets smaller. So that's indicating the localization of the depolarization at synapses. They're small and they're local, relatively speaking. They are also graded. That is to say, there can be small EPSPs and big EPSPs, depending on the number of receptors and the number of activated receptors, the amount of neurotransmitter that activates those receptors. So small, graded, local are postsynaptic potentials. By graded, I mean they aren't all or none. When you take a test, you get a grade. Maybe it's 100%, maybe it's 90%, maybe it's 80%, maybe it's 0, but it's not either 100 or 0. It's somewhere between, typically, 100 and 0. That's what makes this a graded potential. It can be 100%, it can be 50%. It's not all or none. You'll see when we get to action potentials why we're making this distinction, because they are not graded. They are pretty much all 100% or none, 0%. If you're a biophysicist, we can talk about these equations that define the distance that this spreads in terms of the resistance of the membrane and the resistance of the cytoplasm. Okay? This is not a biophysics class, we're not going to do biophysics, but there is biophysics that explains this exponential decay in space. It's an exponential decay. IPSPs are the same sort of thing, only reversed. Here's a typical resting membrane potential. Here's where the neurotransmitter release. This might be a GABAergic synapse, activation of GABA A receptors, influx of chloride, hyperpolarization that decays with some time course back to the baseline. Now, there is a point here I want to emphasize, just to be clear. This is looking at the membrane potential as a function of time, and this is a time exponential decay. This is looking at the membrane potential, this is an EPSP, as a function of distance, not time. And it also has an exponential decay. So you'll see exponentials come in here in many flavors, but don't get confused between distance in space and the time dependence of an event. Okay? They can be confusing. And I want you to, you should look at the x-axis. Are we talking about distance, space, or are we talking about time? So let's start here. These are EPSPs that are graded. A weak stimulus gives a small EPSP. A strong stimulus gives us a strong stimulus gives a large EPSP. Graded EPSPs. This is just showing that this is the same information here as here, right? as you go further away from the synapse, the size of the EPSP is smaller because of that spread, the exponential decrease in amplitude as you go further away. It's sort of like sound, right? My voice is loud here, but it's less loud over at the other end of the room because the sound has spread in space as we've moved from one location to another. Talia?
So the bottom graph, is it showing also like the time that the signal takes to get there? Or
No.
is it kind of two separate graphs?
These are two separate stimuli. It is showing the fact that, it is showing some time-based information. It's showing that EPSPs last a few milliseconds.
But we could just cut the graph in half, basically.
You could just cut this graph in half this way, and there would be two completely valid figures here. Right? This stimulus gave this EPSP. An infinite amount of time might have happened, and then this stimulus gave this EPSP. So we've been looking at EPSPs and IPSPs one at a time, but remember, we're talking about thousands on a given neuron. So we're looking at the response of the yellow neuron to just one input. And some of them are excitatory, and some of them are inhibitory. But there isn't just one happening. There's hundreds or some thousands, maybe tens of thousands. Right? This dendrite, which has been cut off here, which would go into the basement of the building, and that dendrite, which would go up into the third floor, and this one here. So these dendrites are big, and they're long, and they're elaborate, and they make room for thousands of synapses that are happening more or less at the same time. So the membrane potential of this cell body is being impacted by multiple inputs that have temporal and spatial differences. The point, remember that there is the axon, and there is the spike initiation zone, initial segment or initiation site or zone, the axon hillock. That's all names for this initial part of the axon. And that's where a lot of the so-called decision-making of this neuron is done to decide whether to fire an action potential and how many to fire. What frequency with which I the neuron, is going to fire, am going to fire action potentials. So this zone of the cell is special. It is more determinant of the output of this neuron than anywhere else, because it is where the action potential frequency and all or noneness are determined. So, question out here: do all synapses influence action potential initiation equally? In other words, does this synapse have the same impact on action potential output from this neuron as this synapse? Does this synapse have the same impact as this synapse? I've seen some heads, I've seen some heads nodding, I've seen some heads shaking. Let's discuss this, let's work this out. Charlie.
There's a summation, wouldn't they both be more effective the closer they are together in space?
Closer they are together, or the closer they are, you're on the right track here.
Okay.
Closer they are to what?
To where
you're on the right track. To where,
the signal is being propagated from.
yes, to where the action potentials are being initiated. These synapses are at the spike initiation zone. They have a relatively large impact on the membrane potential of the spike initiation zone. These synapses are centimeters away, some of them. These synapses, these synapses are way out here. They're not, they have some impact, but they have less impact on the membrane potential of the spike initiation zone than the synapses that are right there. So the answer to the question is no. Some synapses have a greater effect on the membrane potential of the spike initiation zone than other synapses. So for example, this synapse right here might have the same effect as 100 of these guys. So it would take 100 inputs out, say out here, to add up to the same depolarization that we got from one synapse here. So now we're going to talk about temporal summation. So here is a synapse, let's see, synapse A, synapse B, and synapse C. C is an inhibitory synapse, A and B are two independent excitatory synapses from two different neurons. So if A is triggered, if we release neurotransmitter slowly, then the EPSP decays completely between. So now Thalia, these two events are different, but we can't just cut them apart. We're really talking about how they are connected to each other. So this EPSP happens, decays completely, and then this EPSP happens and decays completely. This is the absence of temporal summation because they have decayed to completeness. But here, if these two synapses are triggered closer together in time, then the second EPSP can be bigger than the first because of temporal summation. The first one, the first EPSP did not decay completely when the second one came. And so the second one adds on top of the first one. And so the second EPSP is bigger than the first because it came soon after the first. That is because it's a time-dependent thing, long time, short time. This is temporal summation. Synapse A fires a certain EPSP. Synapse B fires a certain EPSP. They're different, but if they happen to fire at the same time, now we get a bigger total response because we have two synapses firing at the same time. Two synapses causing EPSP at the same time. So this is what's called spatial summation. Two different synapses happening at each having a EPSP of about this size. This is the A EPSP, this is the B EPSP. When they happen at the same time, so there is a time dependence here, but this is two different synapses firing at the same time, and we call that spatial summation. So temporal summation is when the same synapse fires very rapidly, one right after the other. And spatial summation is when we have two different EPSPs. And frankly, you can get an EPSP and an IPSP happening at the same time. And this is also spatial summation, although you might say, well, that's spatial subtraction. if we're at the spike initiation zone, and we have both temporal and spatial summation, so temporal summation, they're close enough together that they're doing the same thing, so that's spatial summation, and we're reaching the so-called threshold for this axon to fire an action potential. So you can see where we're going next is action potential generation. We'll talk about what threshold is in a minute. But the point is, one EPSP almost never reaches threshold. It requires spatial and temporal summation. So even this synapse, let's just say this cluster of synapses right at the spike initiation zone, any one of them might not trigger this action potential, an action potential in this axon. It might require spatial summation, so 3 of them, let's say, firing at, releasing neurotransmitter at the same time, and temporal summation, each one happening in rapid succession, in order for threshold to be reached and action potentials triggered. Okay, so the idea of, this is an important physiological concept, temporal and spatial summation. Are there any questions? Yes?
Could you explain block 4 again as to why it
Block
is so hard?
So in here, we have 2 excitatory synapses that are each, there's temporal summation, A and A are happening close enough together in time that we have temporal summation of the A synapse. We have temporal summation of the B synapse. And these are close enough in time that we have spatial summation of the A and the B synapse. So A is, we have temporal summation, spatial summation to a large EPSP, in fact, an EPSP large enough to get to threshold. Other questions? Okay, so now we're transitioning to action potentials. Action potentials and synaptic potentials are the language that your brain speaks, right? The frequency and pattern of action potentials is information in your brain, right? So the sound of my voice is being converted by your ears into action potentials, which your brain then interprets as language. The sight of the screen is being converted by your retina into action potentials that your brain then interprets as an image. The image isn't in your brain. The action potentials are in your brain. The sound is not, the sound is in your brain, but the fact that your brain is the sound is not what's being triggering anything in your brain. The sound is what's triggering stuff in your ear, and it's the action potential that is what the information is in your brain. So this concept of understanding action potentials and synaptic potentials, this neurophysiology is the information in your brain. And we'll talk later in the course about how your eye converts photons into action potentials. And we'll talk later about how your cochlea converts sound into action potentials. But we have to understand action potentials before we get there. And so some of this is building on self-is. So here's a resting membrane potential. And it's not labeled because it could be -60, -63.2, -74.7, whatever. Some negative number, depending on the relative permeabilities of sodium, potassium, a little bit of chloride, a little bit of calcium, all of that adds up to make a resting membrane potential. So the equilibrium, this is, the equilibrium potential for potassium is somewhere down here. The equilibrium potential for sodium is somewhere up here. These are rounded off. Milliseconds, so we're talking about very short periods of time. 1, 2, 3, 4, 5 milliseconds on this graph. 5 1,000ths of a second. Okay, so here, this is an action potential. It's basically one of these spikes expanded in time so that we can see it better. So each one of these, this is actual data from a nerve, a neuron. This is a cartoon blowing up each of those spikes. Threshold, so this is a EPSP. Let's just say it's a summated, both temporal and spatial summated EPSP that has brought this neuron to threshold. When the neuron reaches threshold, this is the action potential. So that's what this signal now is what we're trying to understand. What I'm assuming is you've got a pretty good understanding of the resting membrane potential, and you've got a pretty good understanding of EPSPs, how they happen and how they summate to reach this value called threshold. I haven't defined threshold yet. I haven't really unpacked an action potential, but that's where we are. Okay? And I'm just introducing some terminology. The amplitude of an action potential is the number of millivolts from its starting point to its peak. Makes sense? And there's some other jargon that I will be using. The upstroke of an action potential is the depolarization phase, the shooting up. The recovery, the repolarization, is also sometimes called the downstroke. Upstroke, depolarization. Downstroke, repolarization. Many action potentials hyperpolarize immediately after the action potential and then decay back to baseline. Not all, but many. This hyperpolarization after the action potential is called the after hyperpolarization. So the jargon gives you a little bit of help. An after hyperpolarization is not the same as an IPSP. Yeah, question, Charlie.
Is after hyperpolarization interchangeable with refractory period?
Good question. The question was, is an after hyperpolarization interchangeable with refractory period?
Or like, are those synonymous?
They are not synonymous, but they are definitely related. You can have a refractory period without an after hyperpolarization, but you can't have an after hyperpolarization without a refractory period. So we'll talk about refractory periods in a few minutes. And this is jargon that I don't actually use very much. Overshoot is just the amount of the action potential that's above zero. So as you learned in self-phys, the upstroke is due to sodium channels and sodium influx. And the downstroke is due to potassium channels and potassium efflux. And so this graph, so that was the self-phys level of knowledge. This graph shows you some of the time course. The sodium conductance, the sodium channel activity increases very rapidly and then decreases relatively rapidly during the action potential, the potassium channel activity, responsible for the downstroke and responsible for the after hyperpolarization, is slower than the sodium channels. Different channels, different proteins. Sodium channels have a fast kinetics, potassium channels have a slower kinetics. Different molecular properties. These properties, sodium channels causing a depolarization, potassium channels accelerating the repolarization and causing the after hyperpolarization, are what make the action potential. So let's elaborate. So here is the small local depolarization. The small local depolarization. If the small local depolarization is big enough to reach threshold, which we'll define on the next slide maybe, or soon, real soon, it opens enough depolarization activated sodium channels, which allow more sodium influx, which allow more depolarization, which open more depolarization gated sodium channels. And we have this very fast positive feedback loop. So if the small local depolarization reaches threshold, we open some sodium channels, sodium influx, depolarization, more sodium channels, more sodium influx, more depolarization, more depolarization, more sodium channels open, more sodium influx, more depolarization. This upstroke is caused by this positive feedback cycle. If the small local depolarization opened enough voltage-gated sodium channels. If the small local depolarization was not big enough, did not reach threshold, it would just decay back to the baseline. That would be just an EPSP that did not trigger an action potential. But here, so 1 was a sub-threshold EPSP. 3 was a sub-threshold EPSP. 4 was a above-threshold EPSP that caused an action potential, and so was 5. Not all EPSPs reach threshold. So threshold is the voltage required to get enough sodium channels to get this feedback loop going. If we only open a few, then those resting potassium channels can bring the membrane potential back down. And that's sub-threshold. Okay, so threshold is the voltage that opens enough sodium channels to fire an action potential. Once we get to that threshold, this cycle just goes until we have no more available sodium channels. They have all been activated, all of them. And so the fact that this goes to completion is what makes it all, quote, all or none. Did I give you this slide on your handout? Yes. Put quotes around all or none, because that's not strictly true, but that is approximately true. If you fire an action potential, it's going to go all the way. So it's not like an EPSP that is graded. It is all or none. Once you get to threshold, it goes. It's like me saying, you sit down to take your quiz, take out your pencil, and you get 100%. Obviously that doesn't happen, because quizzes are graded and action potentials are all or none. Maybe the analogy's not so good, especially when you have a quiz coming up this weekend. Graded potentials, all or none. This graded potential did not reach threshold, and it decayed back to baseline. These two EPSPs reached threshold, and they both fired exactly the same action potential. Questions about the upstroke? Because what we have done is we have understood up to about here. So now, just to recap where we are and what you know the basis for the resting membrane potential. You know the basis for summated EPSPs and IPSPs, but we're focusing on EPSPs. And now you understand the basis for this phase of the action potential. Okay. After sodium channels activate, with kinetics that are slower than the cycle that activated them, they go into a inactivated state. They have an intrinsic stop mechanism. It's those of you who have studied receptors are thinking, is this like desensitization? And the answer is, yeah, it's like desensitization, but the mechanisms are different. So sodium channels inactivate after they activate. What is the difference? So what is the difference between a closed sodium channel and an inactivated sodium channel? Is that closed sodium channels can open and inactivated sodium channels can't. They have to get back, they have to go from inactivated back to closed in order to open. Inactivated channels are non-permeable. Sodium's not going through them. They're inactivated. But I'm going to ask you to be precise about your use of language. A closed sodium channel is a sodium channel at rest, ready to go into this cycle. An inactivated sodium channel is one that has just been used. It is refractory. It can't go into this cycle until it gets back into its resting closed state. So I didn't, on the problem set, some of you used closed when you meant inactivated, and I didn't take off for that because we hadn't had this class yet. But now I'm asking you to be precise about closed versus inactivated. Okay, so let's do this and then maybe take a break. So this is a kinetic scheme. We've got sodium channels that are closed, open, and inactivated. At the resting membrane potential, most sodium channels are closed because inactivated sodium channels have recovered back to the closed state, and the kinetics of opening are such that, well, they don't like to open at the resting membrane potential, and so they stay closed. Every once in a while one will open, but the opening rate is very low, the closing rate is very high, the recovery rate is very high, and so most sodium channels are here. Immediately after depolarization, the opening rate gets high, and so channels open. And they might open and they might go back and forth between this thing, between these two states. But there's a lot more openness here than there is here. So immediately after depolarization, the channels open. This is the same as the depolarization causing them to open. This arrow and this arrow are similar arrows. Yeah?
At the resting membrane potential, when the sodium channel happens to open when it's rare, you said, is that the cause of like the sodium leaks?
That is one of the causes of sodium leak. There are leak channels, and there are a
But that
few,
is not, leak channels are
a different channel, a whole different protein. In fact, some people say there's no such things as leak channels, that all of this, that we can explain all of sodium leak by this, but I'm not sure that that holds up. Did you hear the question over there at the other side of the room? The question was, does this little bit of opening, is that responsible for the so-called sodium leak at the resting membrane potential? And the answer was, this probably the most parsimonious answer is, it's responsible for some of it. So immediately after depolarization, the opening rate increases and channels open. And they might open and close, but they open. Eventually, they spend enough time in the open state that they go into this closed, this non-permeable, inactivated state. So this arrow is the same as this arrow. And if we stay depolarized, the channels will stay inactivated. It's what they call an absorbing kinetic state. If the membrane is depolarized, eventually all the channels will end up over here. But if the membrane repolarizes, which remember, the membrane repolarizes, we haven't gotten there yet, but eventually the membrane repolarizes and hyperpolarizes. When the membrane is repolarized or hyperpolarized, then the protein can transition from an inactivated back into its resting closed state. These are both non-permeable. Sodium's not passing, but they're different. This doesn't happen, but this does. At a depolarized, immediately after depolarization, we go from closed to open. Long term, a couple of milliseconds, that's long. A couple of milliseconds after the depolarization, the channels end up over here. And this is where they would stay unless we have repolarization to allow them to recover. Let's take a break, and we'll transition from voltage-gated sodium channels, which are responsible for the upstroke, to voltage-gated potassium channels that are responsible for the repolarization. Let's take a break. Talked about the resting, I'm going to do this again. Resting membrane potential, EPSP, upstroke. We have gotten to the peak of the action potential. Sodium channels, so we're still about here. Sodium channels, the number of open sodium channels is low because many of them have transitioned from open to inactivated. So during this entire repolarization phase, sodium channels are inactivating with some kinetics. So right here, the membrane is depolarized. This has happened. And this is happening a lot.
The inactivation, is that like over time, eventually they inactivate, or is that certain voltage they inactivate?
It is a voltage and time-dependent phenomenon. So is activation, actually. Activation is a voltage and time-dependent phenomenon. Inactivation is slower than activation. That's what this word means. But what's also going on during this phase, in addition to sodium channel inactivation, is we have potassium channel activation. They activate, so the kinetics of potassium channel, so this is time, so this is looking at the time course of voltage-gated potassium channel activation. It happens a little bit slower than the inactivation of sodium channels. It's happening about the same time. So as sodium channels are inactivated, potassium channels are activating. Voltage-gated potassium channels are activating, opening, potassium flows out, outflow, efflux of potassium, more negative on the inside. It assists in the repolarization. So the repolarization and the after hyperpolarization is due to two things. Sodium channels are inactivated. And potassium channels, voltage-gated potassium channels, are activated. The resting potassium channels are still there. So here we have two kinds of potassium channels working for polarization. We have the resting potassium channels and the voltage-gated potassium channels doing their thing, and that's what makes the membrane potential after the action potential hyperpolarized relative to rest. Two types of potassium channels, one type of potassium channels. Rest plus voltage gated. And then the voltage gated channels, which were activated by depolarization, close with some kinetics. And as the voltage gated potassium channels close with some kinetics, we're back to where we started. Sodium channels are recovering. Potassium channels are closing. And we're back to where we started. We've closed sodium channels, closed voltage-gated potassium channels, resting potassium channels, open. A few leak sodium channels, open, which makes this around minus 70 millivolts, plus or minus. Okay? So we've done the action potential, again, with a little bit more detail than what you got in self-phys. So I want to finish this class with some challenge questions. We're going to do 2 challenge questions, and then if there's time, we'll do it quicker. So this is pretty interesting. Let me just read through these. Fugu in Japanese, or pufferfish in English, have a toxin. They express a toxin called tetrodotoxin. And tetrodotoxin is maybe the Earth's most perfect toxin. That is to say, it has one effect. It has no side effects that anyone ever knows of. So that's what makes it perfect. It's not a good thing, it kills you, but it's a perfect toxin. It blocks voltage-gated sodium channels. Pufferfish use this as a defense, along with their spines. In Japan, pufferfish is a delicacy. because when you eat it, it causes a little bit of numbness in the lips and in the tongue. It's a little bit risky, because if the chef who prepares the fish does it badly, you die. So there's some, you know, gambling, which is, there's a gambling thing in it. So you're gambling with your life, you're trusting this chef to have done it right, and then you get this interesting sensation in your mouth. So it's a delicacy. The chefs who prepare fugu have to train for years and years before they're allowed to serve it to anybody else. Yeah?
What's the lethal dose?
You mean in terms of micrograms per kilogram?
Yeah.
Tiny. We could look that up. I don't know. It's micrograms. Okay, so here is the world's perfect toxin, a blocker of voltage-gated sodium channels. So now I want you to work on these challenge questions. Does this toxin affect the resting membrane potential? And if so, is it a depolarization or hyperpolarization? Does this toxin affect the amplitude of action potentials? And if so, does it increase or decrease them? That's the direction. And what does this toxin do to the threshold for firing action potentials? So work with your neighbor, come up with a plausible answer to these three questions. I'll give you 5 minutes to work on all 3 questions. Does this toxin affect the resting membrane potential of a nerve that is bathed in tetrodotoxin? Chelsea's saying no. Why not?
Because the membrane potential has to reach threshold before the voltage-gated sodium channels do anything.
Okay. But at rest, we're even before the nerve even thinks about threshold, is the resting membrane potential affected by this toxin? So that, I can understand your answer, and I think it is correct, but it's not the only correct answer. Remy?
I said no because at the RMP, the NA channels are closed, completely closed, so if it blocked the channels, it wouldn't matter, because like
Okay.
it would matter afterwards, but not during.
That's a good answer. There's a but. Somebody want to argue the other? Sophie?
We said yes, because there's like the weak sodium, which you mentioned previously, and so there would be a tiny hyperpolarization because no sodium would flow in.
So the answer is yes. I mean, no, it wouldn't affect the resting membrane potential because, quote, all the voltage-gated sodium channels are closed. But they're not all closed all the time because there is this very small effect that Sophie was remembering. And so this toxin would prevent even that small effect. And so you might get a very small hyperpolarization. Maybe too small to measure. So you can see, but that's why this is a challenge question, is because it has 2 correct answers. Okay? Does this toxin affect the amplitude of action potentials? Somebody who hasn't answered the first question, first 2 questions. Charlie.
You said that yes, it causes the amplitude to decrease, and it inhibits the likelihood of propagation because the action potential is like a more or less an all or nothing, and when the amount of channels you have is less than that of a normal state, then the all is going to be less so.
Exactly. That's a good answer. The all of an action potential is determined by how many sodium channels we have ready to participate in this all. If we block half of the sodium channels with tetrodotoxin, we have less sodium channels to give their all, because half of them are blocked, and the amplitude would be lower. I mean, what Charlie said was a good way to say it, I just said it with slightly fewer words. Clear? What does this toxin do to threshold? Is it easier or harder for this neuron, bathed in tetrodotoxin, to get to threshold given some EPSP summation and fire action potentials? So somebody, not Charlie, not Sophie, not Chelsea, not Remy. Joe.
Wouldn't it be harder for it to reach threshold
It
just
would.
because there is not as many things to fire, I guess?
There's not as many sodium channels available, because half of them, let's say, have been blocked by tetrodotoxin. So remember, threshold is the voltage at which you get enough sodium channels to make an action potential. If you block half of them, you have to open. Let me just see if I can use numbers. Let's say you've got a neuron with 100 sodium channels, way too small. You have to open 10 of them to get threshold, and then you get the positive feedback and opens all 100. So 10 is the number required to reach threshold. 10% of all of them have to be opened by the EPSP to get to threshold to fire all of them. Now let's block half of them. So we only have 50. But you still have to get 10 of them open to get to threshold, because threshold is determined by a number, not by a percentage. So 10 is 20% of 50, as opposed to 10% of 100. So you had to open 20% of them to get to an action potential. The action potential would be smaller because of this question. And threshold would be higher because we have to open 20% of the available sodium channels, not 10%. Okay? Question, Charlie.
Wouldn't it not actually affect the threshold? It would just affect the ability of the cell to get to that threshold?
That's the same thing.
So the threshold's not a voltage.
Yeah, it is. The threshold is the voltage necessary to get enough sodium channels to fire an action potential.
But that voltage wouldn't change from normal, would it?
Yeah, it would. So basically what I'm saying is, if we block half of these sodium channels, we have to get this much of an EPSP, not this much of an EPSP, to open enough sodium channels to cause this. So you die when you eat tetrodotoxin because your nerves get you become paralyzed. Your motor neurons stop functioning, and so you become paralyzed. You die, mostly you die from respiratory paralysis. Your brain can't tell your lungs, your diaphragm to contract, and the first thing to go is you, because you're no longer breathing. JP, did you have a question?
Would it change the difference between threshold and resting membrane potential, or would
Yeah. So the resting membrane potential would be affected very little, and threshold, so the distance would be affected. We're not done. I've got another challenge
would
question.
threshold actually increase?
Threshold would increase. Okay, here's another challenge question. Let's work on this for the last few minutes. So this is another interesting toxin. You die if you not eat this toxin, but if somebody stabs you with this toxin, you die. Poison dart frogs secrete a toxin onto their skin. It's called batrachatoxin. That does two things. It prevents sodium channels from inactivating, and it makes the voltage at which they activate more negative. They activate at more negative voltages, and then they don't inactivate. That's what batrachatoxin does. And indigenous Indians in Central America use this as a poison on their poison arrows to paralyze monkeys and birds. You can eat it because your digestive system breaks it down, unlike tetrodotoxin, which you can't eat. Okay. Work on 1 minute on what does this toxin do to the duration of action potentials and what does it do to threshold. What does, oh, and by the way, these toxins, these animals, these frogs produce batrachotoxin because of what they eat. If you bring these frogs into a zoo and give them zoo chow, or whatever for frogs, they stop being toxic. Anyway, what does this toxin do to the duration of action potentials? Anyway, Remy.
It increases the duration, it just like keeps the polarization going because there's no stopping point, because there's no inactivation.
Inactivation was part of what terminated the action potentials. You get rid of inactivation, action potentials don't terminate as fast, so they stay depolarized longer. It increases the duration of action potentials. That's the right idea. What does it do to threshold?
Decreases the threshold so it's easier to reach.
It's easier to reach. It lowers threshold. So now we have neurons that are hyper-excitable. They excite when they weren't supposed to, and they stay excited much longer than they were. And this is hyper-excitable, and it causes the animals to go into a rigid, hyper-excited state, and birds can't fly, and monkeys can't hold on to the trees, and they fall to the ground, and the Native Americans collect them and eat them. So we've talked about a delicacy, and we've talked about a toxin. There are some clickers, which are on Moodle, which we're not going to do because we've run out of time, but you could do these as homework. Let's stop here. I'll be happy to answer questions if you have time now. Remember, some of you are coming to lab today at either 1 or 4.